All right, Ashley, have a seat. Tell us about the ring. All right, Lisa, got your notes? Let's go ahead
Teachers,
and
please
get right to
excuse this
chapter
interruption. Students, please pay attention. Through social media, there's a lot of talk about the clowns, the angry clowns and stuff going on. Let's make this perfectly clear. There will be no clown mask at any time on this campus. There are never any masks allowed during Halloween also. Please remember that. We dealt with some people yesterday. I now have a clown mask and they were disciplined. Please. Do not get yourself in trouble by bringing, wearing, or even talking about a clown mask. I guess you can talk about it, but don't bring it. Secondly, there's way too much trash out there on this campus. We are failing. We don't want to rope off the whole campus. And here's Mr. Positive.
This is just a reminder for any college visit. It is optional and it is up to the teacher's discretion if students can go to the college meeting, as these are optional. The students must get permission first from the teachers in order to go to the college meeting.
Okay, I'm going to assume that's it. All right, so we get right to chapter 3, which is a continuation, essentially, of chapter 2. In chapter 3, we now take a look at two-dimensional kinematics. Chapter 3 is actually a short chapter, and it's basically divided into 3 parts. The first thing that we do is we take a look at the notation that is necessary to describe position, velocity, and acceleration in 2, or if necessary, 3 dimensions. And then afterwards, we take a look at 2 very important cases of two-dimensional motion that occurs near the surface of the Earth. Either you need to take your sweatshirt. Okay, but first, the notation used to describe position, velocity, and acceleration. All right, so let's say that I have two-dimensional space. So right here is the x direction. If you want to think of this as horizontal, that's fine. And then right here is the y direction. If you want to think of that as vertical, that's fine. And then I have an object that is moving around in some manner in two-dimensional space. Let's say that when we start the clock, the object happens to be right here. So this then means that right here, drawn from the origin to that point, is the initial position vector of the object. We always use the letter R to describe position when talking about a 2- or 3-dimensional case. So then therefore, if this is the initial position of the object at time 0, this is the initial position vector. We then label that as an R0, like so. Okay, now that initial position vector has components. I'm not going to draw the components here on the board because it would be kind of messy if I did. But right here is the component of the initial position in the x direction. Just like we did back in chapter 2, we think of that as x0. Right here is the component of the initial position in the y direction. We think of that as y0, just like we did back in chapter 2. So in component form then, therefore, the initial position vector r0 is written out in the following way: x0 I hat plus y0 j hat. So. Okay, and then some time interval goes by and the object is moving around in some manner. After the time interval goes by, let's say that the object happens to be right here. So then, therefore, relative to the origin, right here would be the final position vector of the object. We just labeled that as r. And then once again, it has components. Right here is a component along the x-axis. We just think of this as x, like we did back in chapter 2. Right here is a component along the y-axis. We just think of that as y, like we did back in chapter 2. So the final position vector in component form is then therefore xi hat plus yj hat. So as I start this process, keep in mind that there's really nothing new here. Still just position, velocity, and acceleration, but it's just going to be all dressed up in its full vector notation. Okay, as the object moves from here to here in some manner, it undergoes a change in position. The change in position is found from the tail to tip method of vector addition. Change is right here. That's delta r. Then here's how the vectors add together using the tail to tip. It's just like it was back in chapter 2. That is, we have the initial position plus the change in position equals then therefore the final position like so. So initial plus change is equal to final. If you move the initial position r0 to the other side, then the change in position, in this case delta r, is the same thing that it always is. That is, it's final minus initial. So. And now we should start describing velocity. First of all, the average, and then we take a derivative to get the instantaneous velocity, and then after that, the process repeats for the acceleration. Okay, but with respect to the velocity, first of all, we have the average quantity. So average velocity. Average velocity is just labeled as v bar. The bar symbol means average once again. If we're talking, however, about a two-dimensional case, then therefore we include the vectors symbol as well. And then this is equal to just change in position divided by change in time. To go from the average to the instantaneous velocity, however, we then take the time interval and shrink it down to 0 size. That gives us our first derivative. So we begin to write out the instantaneous velocity in the following way. The instantaneous velocity is just written as v, and it is then therefore the derivative of position with respect to time. And then here's how we write it in component form. What I'm differentiating here with respect to time is the position vector r up on the top board. So let me take what I wrote up there on the top board and then plug it in the following manner. Derivative of position with respect to time begins to look like this. And then here's what happens when I differentiate the quantity there in parentheses. The unit vectors I hat and j hat are constants. They always have the same magnitude of 1, and they always point in their respective directions. So when I differentiate the quantity here in parentheses with respect to time, I'm just going to be differentiating right here the position in the x direction with respect to time, and then similarly in the y direction. It just looks like this. So, where right here is now the velocity component in the x direction. We label this as v sub x. Right here is the velocity component in the y direction. We label this as v sub y. So then therefore, we just have a v sub x I hat plus v sub y j hat, like so. So as the object on the top board is moving around in two-dimensional space in some manner, at some instant, boom, it has some instantaneous velocity vector. Thank you. Write yourself a pass and then bring it up here for me and I'll sign it for you, okay? So while the object is moving around in two-dimensional space, boom, at some moment in time it has an instantaneous velocity vector. Just generically, let's say it looks like this. And then the components are just simply drawn in the following way. Right here is v sub x in the x direction. Right here is v sub y in the y direction. So this right here in component form is just describing this vector here. And then we just repeat the process here one more time to describe acceleration. First of all, the average value, and then after that, second derivative for the instantaneous. Okay, first of all, the average. So the average acceleration is written as a with the bar symbol above. However, still have the vector sign here for this two-dimensional case. And this is equal to change in velocity delta v with respect to time. Okay, a little bit of notation there with respect to the change in velocity. You are late, by the way. That's right. Here you go. On your own paper, please. Thank you. Okay, the notation here in the numerator is as follows. This is change in velocity. So change in velocity is equal to final minus initial. The initial velocity is still written as v0 as it is in the one-dimensional case. If I was going to write that vector in component form, it would look exactly like this. You would just have a little subscript 0 associated with the initial velocity components. Okay, then just now shrink the time interval down to 0 size to describe the instantaneous acceleration. So you pick up another derivative here. The instantaneous acceleration is just a now with the vector symbol This is derivative of velocity with respect to time. So in component form then, what I'm differentiating there with respect to time is this quantity right here. That's the instantaneous velocity. So if I now differentiate that with respect to time, just to show how the components here work, like so. Once again, the I hat and j hat unit vectors are constants, so I don't have to worry about them when I take derivatives. So I'm just going to be differentiating right here the velocity in the x direction with respect to time, and then right here in the y direction as well. That gives us something that looks like this. Like so. And right here is now the acceleration in the x direction. This is just labeled as a sub x. Right here is the acceleration in the y direction. This is labeled as a sub y. So a sub x I hat plus a sub y j hat. So as the object is moving around on the top board in two-dimensional space in some manner, at some instant in time it has an acceleration vector. Just generically, that acceleration vector, say, looks something like this, where it has an x component, like so, a sub x, and a y component, a sub y. So once again, there's nothing new here. It's just everything just dressed up now, position, velocity, and acceleration, and it's full vector notation. The way that I've described it here is for a two-dimensional case, but if you had a three-dimensional case, then all that would happen is that all of these quantities here would just have an additional term. So for example, up here on the top board, if this is the xy plane, then the third dimension, or the z direction, would be perpendicular, like so. The unit vector associated with the z direction is called k hat. All of the quantities here would just have that additional term.
Can you explain how you found the derivative?
Yeah, so just differentiating this guy here in parentheses with respect to time. When I do, I don't have to worry about the I hat and the j hats, because those are numbers, they're just constants. So I'm just differentiating the velocity with respect to time first in the x direction, that's there. And then secondly, derivative of velocity in the y direction with respect to time, that's there. These guys here are the acceleration components, a sub x and a sub y. So it's just the same thing as we saw in one dimension, but now just dressed up with its full vector notation.
You said that the not vector.
So it would be, you'll see me do this when we get to the specific cases in a little while, but it's the same thing as this, just with a little naught symbol associated with it, that's all. Okay? Okay, let me erase all this junk. That's essentially what it is, it's all junk. And now, for the remainder of the chapter here, we take a look at two very important cases of motion that occurs in a plane near the surface of the Earth. Let me get rid of this red pen, it's dying. Okay, so now two important cases. Two-dimensional motion. Near the surface of the Earth. Okay, the first of these two cases is called projectile motion. Okay, so what is a projectile? Well, very simply, this right here is a projectile. So what we want to describe is the kinematics of this motion, position, velocity, and acceleration. When we do, just like we did for an object in free fall back in chapter 2, what we'll now do here for a projectile in chapter 3 is we're also going to neglect air resistance. We'll neglect air resistance as others. Now, to describe the kinematics of this very important type of motion near the surface of the Earth, what we basically need to know is the acceleration of a projectile. Because if you can find the acceleration of a projectile, then presumably you can integrate to find velocity as a function of time, and then integrate again if necessary to find position as a function of time. So whenever describing the kinematics of some motion, what you have to find is the acceleration. Once you know what the acceleration is, then in theory, everything else can be described. So, to describe the kinematics of a projectile, we need to find the magnitude and direction of the acceleration. Because then once we have that information about the acceleration, then everything else, that is position and velocity as functions of time, about the projectile can be found. So how do we find the acceleration of the projectile? Well, what I'm about to show you is a classic physics demonstration that all introductory students see. The demonstration has somewhat of a funny name, and it's called the Monkey Hunter demonstration. The Monkey Hunter demonstration, as it's called, is designed to illustrate the acceleration of a projectile. Okay, here's how I'm going to approach the demonstration. First of all, I need to explain it to you. After I've explained how the demo works, then I'll perform it. And once you see the result of the demonstration, then we'll go through exactly how it gives us the acceleration of the projectile. So first of all, let me explain the demo itself. Okay, first of all, what is the monkey? Well, the monkey is this block of wood right here. And at the top of this block of wood, I have right here a metal strip. Okay, and then the projectile is going to be this steel BB right here like so. And what I'm going to do immediately is take my projectile and load it right here into the barrel of this gun. And yes, this is a gun that I will be firing in just a few minutes. So, okay, now, take a look up here on the ceiling. Up on the ceiling right there is a little screw that's just been screwed into the ceiling tile. But surrounding that little screw right there is a long coil of wire, which then stretches down like so to the gun itself. And when the gun is on, before I fire it, but when the gun is on, it completes a circuit. And that then up there on the ceiling becomes an electromagnet. And that electromagnet then gets attracted right here to this metal strip on the monkey. Let me show you what this looks like. So I'm not going to fire the gun yet, but I am going to turn it on. So to turn it on, like so. And now to complete the circuit for my monkey, what I actually have to do is take this wire that is right here, and I have to place it into this notch that is right here on the barrel of the gun. The gun itself, by the way, is electrified. Like so. She's flinching away. She can see the sparks here associated with the barrel of the gun when I do this, okay? It kind of looks impressive, but it's actually only a couple of volts. It's no big deal. I can go ahead and touch it perfectly fine. And what I just did is I put right here this wire into the notch here in the barrel of the gun. When this has been placed as it is, this means that the circuit is now closed and that is on. So now what I'm going to do is take my monkey here, and I'll put my monkey up here on the ceiling. He'll stick to the electromagnet. Like so. Stay. 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 Just like that. So he's fallen, by the way, and hit me in the head a few times. Okay. Right now, watch what happens to the monkey up on the ceiling, however, when I pull this wire here away from the barrel of the gun. Notice that the monkey falls like so. So when I pull the wire out from the barrel of the gun, that basically opens the circuit, and that then shuts off. So now when I fire the gun itself, and by the way, the gun is actually just a blowgun. All I have to do is blow into it. When I fire the gun, while the BB is in the barrel of the gun, it's not a projectile. It does become a projectile, however, the instant that it emerges from the barrel of the gun. But when it does, it kicks this wire out of the way, which then opens the circuit, and as you saw, the monkey falls. So in other words, the instant that the BB becomes a projectile, the monkey begins to fall from the ceiling. And now what I want to do is aim the gun such that I can hit the monkey. I basically have three choices. Number one, I could lead the monkey a little bit. In other words, I can aim below him when he's up there on the ceiling. That's my first choice. Or I can, secondly, aim behind the monkey a little bit. In other words, I can aim slightly above him when he's up there on the ceiling. Or my third choice is to aim directly at the monkey when he's up there on the ceiling. So then therefore, how do I aim the gun to ensure that I hit the monkey? What do I choose to do? Can anybody tell me? Aim below it?
Wants to aim directly at it.
Yes, I aim directly at the monkey when he's up there on the ceiling. So now let's watch the entire demonstration. So, what I gotta do first, start to sound like so. Crank that over. And then close the circuit by placing this wire like so. Let me make sure it's on. There we go. Like that. Okay, now I take my monkey. Like so. It kind of came loose a little bit here when he hit the floor the first time. By the way, watch this. This is called engineering. It's called engineering. And now, let's go ahead and stick him back up there. My bad knee and all. So, stay. Come on. Okay, don't rotate. Just stay. No, don't rotate. Because everything that's gone wrong with this experiment, everything that can go wrong with this demo has gone wrong in the past, including me falling off the ladder. That happened 10 years ago. Right, come on, stay. Okay. Don't ding me in the head on the way down. All right, now I'm going to get this out of the way. Now I'm just going to tell you ahead of time that if it doesn't go right, it's because my aim is bad, not because of physics. What I have to do is I have to aim directly at the monkey when he's up there on the ceiling. Now, this is off a little bit, I have to adjust. That's what the clamps here are for. So, a little high. That's pretty good. I can fire it, yeah, I'm just making one final minute adjustment here. As you can see, it actually is a rather small target. Okay, that should be pretty good. Okay, so now, don't watch me, watch him. And by the way, watch for where the BB goes, I gotta find that afterwards. 1, 2, 3. Oh! So, it hit, right?
Yeah.
Okay, good. I couldn't see because the barrel of gum is in there. All right. Okay, let me go ahead and find that. Let's make sure that's off. Thank you very much. I'll show it to you again at the end of the period, by the way. There. All right, so how does this demo give us the acceleration of a projectile? And here's how it works. First of all, right here is horizontal, here's vertical, and by definition what we're going to do is we're going to say that the barrel of the gun is the origin. And then right up here on the ceiling, like so, is the monkey to begin with. So then therefore, with respect to the origin, let me get here another color mark. So then therefore, with respect to the origin, right here is going to be the initial position vector of the monkey. Let's call this R0 monkey. So, the projectile, however, by definition, begins here at the origin. That's how I'm setting it up. So the initial position of the projectile is equal to 0. So R0 projectile, by definition, is equal to 0. Okay, then we have the initial velocities of the objects. First of all, the initial velocity of the monkey is 0 because he just drops from rest. So V0 monkey is equal to 0. Now the initial velocity of the projectile is definitely not 0 The magnitude of the initial velocity vector of the projectile basically depends upon how hard I blow into the blowgun. We don't know what that value is, but we do know its direction. As I described, I was aiming directly at the monkey when he was up there on the ceiling. So then therefore, the initial velocity of the projectile, that vector, looks like this. Like so. So this right here in green, pointing in that direction, is V0 projectile. Okay, and then, as you saw, the collision takes place here at some distance above the floor. The projectile moves through its path like so, and collides with the monkey. So because the two objects collide right here, what this then means is that at the end of the demonstration, the two objects have the same final position. They collided together. So right here is the final position vector of both objects. Let's just label that as R. Okay, and then we get to the accelerations. We already know what the acceleration of a monkey is because it's in free fall. We studied that, of course, back in chapter 2. So the acceleration of the monkey is what we know. That's just equal to g straight downwards at 9.8 meters per second squared. Here in vector notation is how we write acceleration due to gravity. Negative j hat just simply means vertically downwards. Okay, the unknown in all of this, what we're trying to find, is the acceleration of the projectile. That's our unknown. Now here's then how I illustrate what the acceleration of the projectile is. All that I have to do is write down the position equation R for both objects and then just set them equal to each other. They're equal to each other because remember that the two objects do collide together. Now the final position equation back from chapter 2, dressed up in its vector notation, just looks like this. Initial position plus initial velocity times time plus 1/2 acceleration times t squared. So just in vector form, this is what our final position equation looks like. And now I just write it down for each object. Let me first of all write it down for what we know. In other words, the monkey. So for the monkey, the position equation R is going to be the following. We first of all have the initial position, right here, R naught monkey. So. Plus then the initial velocity of the monkey times time t. Now remember that the initial velocity of the monkey is 0, it's dropped from rest. And then we have our acceleration term plus 1/2 a monkey t squared. Okay, now I just write down the equation for the unknown. Okay, that's the projectile. So for the projectile, we have its final position, the same value of r, equal to first the initial position of the projectile, which is 0, plus v0 projectile times time t, plus then the unknown, 1/2 the acceleration of the projectile, t squared. So I'm just writing down the equation here for both objects. Okay, Ari, just go ahead and put it right here. We'll just leave it like this. Thank you. Okay, and now I'm just going to set the equations equal to each other. What I'll do is I'll write the unknown, the projectile on the left-hand side, and the known, the monkey on the right. So first of all, for the projectile, the unknown, we're going to have v0 projectile times time plus 1/2 a projectile t squared. This then equals, for the monkey, r naught monkey plus 1/2 a monkey t squared. And now take a look at the following two terms. Take a look at this term right here for the projectile, and this term right here for the monkey. Refer to the diagram above. If you take this green velocity vector here, v0 projectile, and multiply it by time t, what is it equal to? Well, it's just equal to r naught monkey. Think of it very simply in the following way. Think of both objects as falling below a line. If neither object accelerated, the monkey would just stay right here, but it's falling below that point. If the projectile, however, does not accelerate, it just moves from here to here in time t. It's falling below that line. What this means is that this distance, r naught monkey, is equal to v0 projectile multiplied by time t. These two quantities are equal to each other, therefore they cancel out from the expression, like so. Once again, the easiest way to think of this is just say to yourself, what happens if neither object accelerates? If neither object accelerates, the monkey just sits there, and the projectile just goes from here to here in time t. So then therefore, this distance right here is equal to speed times time. These terms cancel each other out. And then you end up with the following result, which probably a number of you suspected anyway. We have right here, 1/2 acceleration of the projectile t squared equals then over here, 1/2 a monkey t squared. The 1/2 t squareds cancel out. You just end up with the following. The acceleration of the projectile is the same as the acceleration of the monkey. Both objects accelerate downwards in 9.8 meters per second squared. If you think about this, this shouldn't be all that surprising. All that this simply means is that it doesn't matter if I take the object and throw it in one dimension like so, as we did in chapter 2, or in 2 dimensions like so, now in chapter 3. In both cases, it's the same Earth. So then therefore the acceleration due to gravity is the exact same value for both at 9.8 meters per second squared straight downwards. There's actually no physical difference between the one-dimensional case that we looked at in chapter 2 and now the two-dimensional case here in chapter 3. Because there's no physical difference between the two, they have the same acceleration, we actually use the terms free fall and projectile motion interchangeably. They mean exactly the same thing. A projectile is a free fall and vice versa. So as I take the object and toss it like this in two-dimensional space, what that means is that the velocity horizontally never changes because there is no acceleration for a projectile horizontally. The acceleration is only straight downwards. The easiest way to wrap your head around this in terms of the demonstration itself is to keep in mind what I said a little while ago. Both objects are falling below a line. They're falling below a line that they would have traveled if there was no acceleration. If the monkey doesn't accelerate, he stays here at this point. But he does accelerate straight downwards, he falls below that point. The projectile itself, if it did not accelerate, would move along this line. But it is accelerating downwards at 9.8 meters per second squared. It is then therefore falling beneath this line. One last basic aspect to the demonstration, I've been describing it here on the board as a two-dimensional type of motion, but of course the projectile as it moves here through the room is moving in three-dimensional space. So is it a two-dimensional motion or is it a three-dimensional motion? It's a two-dimensional motion for the following reason. Let's say that I define things as I did, where V0 projectile here is in the XY plane. What then therefore is the Z component, that is like so, of this initial velocity vector equal to? It's equal to 0. However, the Z direction is the horizontal direction. There's no acceleration horizontally for a projectile. So then therefore, as the object moves here in space, what is the velocity component in the Z direction always equal to? 0. It's always equal to 0. In other words, it's confined to the XY plane. So the motion itself is planar, even though the object itself is moving in the three-dimensional space that it's from. Okay? So the monkey hunter demonstration basically illustrates that the acceleration of a projectile and an object in free fall is exactly the same thing, 9.8 meters per second squared. It's the same Earth. That shouldn't be all that surprising. That's what the demonstration illustrates. Okay, now that we know what the acceleration of a projectile is, at this point, describing its kinematics is actually quite easy to do. I'll do that, however, after we take a short break here. Let me go ahead and do that now. I have to take the attendance anyway. Where are my glasses? Did I leave my glasses over there?
Yes, you did.
Okay, good. All right, during the break, just be careful of the gun and be careful of the wire here on the floor.
Careful with the finger in it. Underestimate.
Is Sam here today?
Stop it once it's beat.
Okay, cool, thanks.
Be good.
He's out of town? Okay. Haley, do you have a question? Sorry, I thought you were asking something.
Would you do? Maybe you shouldn't have done that. Whatever you did.
I have.
The next time, maybe you should do something.
Your iPhone.
Do the IOL homework.
Let's see, let me grab this. All right. So now the kinematics of a projectile. Okay, now that we know that the acceleration of the projectile is just downwards at 9.8 meters per second squared, describing position and velocity as a function of time is really easy to do, because we've already seen it back, for example, in chapter 2. However, we begin to diagram out the situation in the following manner. Here's kind of how we define things. Okay, first of all, let's say that right here is the origin. Well, let's say that I launch the object away from the origin. So let's say, for example, that I launch it like this. Now, I'm not going to draw the initial position vector here on the board, because otherwise the diagram is getting a little messy. But the initial position of the object will be drawn from the origin to here, like so. However, we do picture its components in the following way. Horizontally, we have an initial position like so, x naught. And then vertically, we have an initial position like so, y naught. And then we take a look at this initial velocity vector. The initial velocity vector of the projectile is just labeled as v naught. The magnitude here, v naught by itself, would be the object's initial speed. And then immediately we start to picture the components here of this initial velocity vector. Here's the x component like so. This is called vx naught. And right here is the y component labeled as vy naught. We also define, by the way, the following angle. This angle right here, referred to as theta naught, is sometimes called the initial angle. It's also sometimes called the projection angle. It means the same thing. And then the object moves through its path like so. And then we just examine what happens at some time t later. Let's say that at that time t, the object happens to be right here. So then therefore its final position vector, I'm not going to draw it on the diagram because otherwise it would be kind of messy. The final position vector would go from here at the origin to this point like so, but we do draw its components. The final component here in the x direction is labeled as such, and then the final component in the y direction is labeled like this. Now at this particular instant, when the object is here on my diagram, its velocity vector v at this moment looks something like this. And that velocity vector has components. We have right here a component in the x direction, v sub x, and a component right here in the y direction, v sub y. So this is how we begin to picture position and velocity as functions of time. And now we get to the actual kinematics equations themselves. When we get to the kinematics equations, we already know what happens here, for example, in the vertical direction. Vertically, it's still the same thing as an object in free fall back in chapter 2. In other words, we still have an acceleration downwards at 9.8 meters per second